So I want to welcome everybody to our APIOS seminar series. And thank you to the speaker for being flexible and giving the talk today, although originally the plan was for the seminar to be given on Thursday, I believe, this week. So Professor Liu, Xiaochuan Liu, I hope I'm pronouncing your name properly,
Very good.
Is a professor at Xi'an Jiaotong University, one of the top universities in China, whose field of expertise lies in the PDE analysis of integrable systems. Many of them come as a home type PDEs. So I'm very pleased to be able to invite him to give his talk today. So please go ahead. And can I remind everybody to mute your microphones and also turn off your video unless you are the speaker, and to put any questions you have in the chat window if you can. Otherwise, you can also speak up and I will call on you to give your question, and we can have a question and answer session at the end. So please go ahead, Professor Liu.
Okay, thank you. Thank you, Professor Nalini. Hello, everyone. I'm honored to be here, attend the Asia-Pacific Integrable Online Seminar and talk about some of our recent works, the Liouville Correspondences between integrable hierarchies. These are the joint work with Professor Over, Professor Chang Zhengqu, and Professor Jin Kang. These works are motivated by the Liouville transformations relating the isospectral problems. It is found that the Liouville transformation between the two isospectral problems of two hierarchies also establish the relationship between their respective recursion operators, and then the relationship between their flows and Hamiltonian quantities. On this topic, we have accomplished a series of works since 2016. In the case of scalar hierarchies, we established the result of Liouville correspondences between the modified Kamas-Holm and the modified KDV hierarchies, Novikov and Savada-Cotero hierarchies, Degas-Paris processes, or DP, and Kopp or Kuiper-Smith hierarchies in our consecutive two papers. In this talk, I want to discuss the case of multi-component hierarchies and present our recent result of Liouville correspondences for the integrable two-component Kamas-Holm hierarchies and the two-component Novikov hierarchies. These hierarchies are generated by the corresponding integrable systems and their respective recursion operators. Here, the two-component Novikov system, which is also known as Gongxue systems, introduced by Professor Geng and Professor Xue in 2009. On the other hand, the two-component Kamas-Holm system is the dual integrable system of the classical Ito system in the sense of tri-Hamiltonian duality. The theory of tri-Hamiltonian duality was developed systematically by Over, Rosnow, Focus, Fuchsteiner in these references. It was recognized that some classical bi-Hamiltonian integrable Soliton equations actually support a compactable trio of Hamiltonian structures through a particular scaling argument. Recombinations of the members of the compatible Hamiltonian triple will probably generate new bi-Hamiltonian equations, which are always called the dual integrable equations with respect to the original Soliton equations. This resulting dual equations are endowed with the nonlinear dispersion and support various kinds of non-smooth solid structures and other non-trivial features. Some typical dual pairs have been established.
Professor Liu, I think we've lost your sound.
Schrodinger equation is known as the Fuchs-Lehner's equation in recent literatures. If one applies this approach to the E2 equations, then the two component Kamas-Holm ecosystem appears. In general, the approach of tri-Hamiltonian duality serves as a somewhat powerful method to discover new Hamiltonian systems from some given ones. However, it apparently seems that not all the Hamiltonian integrable equations admit such structures, such as the Novikov equation, the D equation, and Genxue system, and so on. As mentioned earlier, the two-component Kamas-Holm system, as well as its Hamiltonian structures, was originally derived by Over and Rosner using the approach of tri-Hamiltonian duality. This system is of significant interest. It is a typical multi-component shallow water wave model and can be used to describe the wave breaking phenomena. On the other hand, it is related to the first negative flow of the AKNS hierarchy by a kind of reciprocal type transformation. In addition, its other mathematical properties, such as the integrabilities, geometric aspects, algebra geometry solutions, well-posed, Bloch phenomena, and so on, have been addressed from different points of views recently. The Genxue system is a representative multi-component integrable system with cubic nonlinearity. It was derived by Geng and Xue by establishing its Lux pair formulation. The Hamiltonian structure was found 4 years later by Li and Professor Xiaochuan Liu in 2013. The Genxue system admits several significant peak dynamics. See the works by Landmark and Smijerski. The well-posedness and the Bloch phenomena were also studied recently. In general, this integrable system, no matter multi-component or scalar ones, have a common characteristic. They support nonlinear dispersive structure. So here is a question: can this Kamas-Holm type system with nonlinear dispersion be related to those classical integrable systems with linear dispersion structures in certain manner? This question is enlightened by the paper from Fuchs-Lehner in 1996. In this paper, it was shown that the Kamas-Holm equation is related to the first negative flow of the KdV hierarchy by reciprocal transformations. This result concerns the correspondence between one equation and the other. Later then, McKean and Lenners in 2003 and 2004 generalized this result to the entire hierarchies. They proved that these reciprocal transformations can transform one hierarchy into the other. In 26, we established the Liouville correspondences between the modified Kamas-Holm and the modified KDV hierarchies, including the explicit relationship between their equations and Hamiltonian functionals. So what is the mentioned Liouville correspondences? Usually, the transition from one isospectral problem to another one through a change of variables can be identified as a form of Liouville transformation. It is then expected that such a transformation can be used to establish an inherent correspondences between the integrable structures of the two integrable systems and serves to relate its flows in their respective integrable hierarchies. In this sense, there exists Liouville correspondences between these two integrable hierarchies. It was noting that for the case of chromosome and KDV, modified chromosome and modified KDV, they are both dual pairs in the trihamiltonian sense. In particular, two Hamiltonian operators for the chromosome and modified chromosome can be constructed from those of the KDV and modified KDV. As a result, the Hamiltonian operators and recursion operators between chromosome and KDV and between the modified chromosome and modified KDV hierarchies will have some inherent relationships which are realized by the Liouville transformations between their respective isospectral problems. So then another question arises. Does this Liouville correspondences only exist between two integrable hierarchies which are dual pair in the trihamiltonian duality sense? With this problem, we begin to study the Novikov and the DP equation. As mentioned earlier, they do not admit trihamiltonian structure. So establishing their Liouville correspondences is more challenging. Nevertheless, using the Liouville transformation between Novikov and SK isospectral problems, we obtain an operator identity between their respective recursion operators. Meanwhile, we found non-trivial decomposition identity for the two recursion operators of the SK hierarchy. Consequently, we established the Liouville correspondence between the Novikov and Sawada-Kotter integrable hierarchy as well. In a similar manner, the Liouville correspondence between de Gasperis processes and Koop-Smeeter hierarchies were also established. It is worth mentioning that in contrast to the approach used by Linus in 2004, the key issue of our method is to establish the operator identity for the recursion operators, combining it with the reciprocal structure in the Liouville transformations, which adheres to the conservative structure of the modified chromosome, the Novikov, and the DP flows. It is also important in some sense that we need to find a proper decomposition identity for the recursion operators and do some delicate analysis for the conservative structure of the integrable flows. Now it comes to the multi-component integrable hierarchies. For those multi-component case, we still expect to be able to establish the corresponding Liouville correspondences between these multi-component hierarchies. It is anticipated that their corresponding integrable hierarchies should also be related to some hierarchies with linear dispersion structure. For the multi-component system, to achieve this goal, we need to overcome several new difficulties. First of all, the integrable structure of the transformed hierarchy in many times is unknown. Furthermore, as in the Scalar case, the proof of the Liouville correspondences relies on an analysis of the underlying operators, which in the multi-component case takes matrix form. So a more delicate calculations to deal with the nonlinear interplay among the various components is required. Secondly, since the dual counterpart of the two-component chromosome is the Ito system, which is a two-component generalization of the KdV equation. In view of the Liouville correspondence between the chromosome and the KdV hierarchies, we originally expected that the hierarchies which has Liouville correspondences with the two-component chromosome hierarchy must be the Ito hierarchy. So is there such correspondences between the two-component chromosome hierarchy and Ito hierarchies? This is our first question. On the other hand, for the Gengxue system, which does not have the dual counterpart, how to find or clarify its Liouville correspondences hierarchy? This is another question. Okay, we begin with the two-component chromosome hierarchy. In 1988, Antonowitz and Foddy studied the isospectral problem of the Heradim type, whose associated general n-component system will possess n+1 compatible Hamiltonian structures. Furthermore, it was proved that such isospectral problems will be transformed into three by this general Liouville transformations one. In particular, this transformation for n equals 2 was employed by Professor Eugene Zhang and Professor Xiaochuan Liu to convert the special case 4, that is the last pair for the two-component chromosome system, into this last pair formulations 5, and then the compatibility condition of the transformed last pair gives rise to this integrable system 6. In view of the structure of the former last pair, this system 6 is recognized to be the first negative flow of its corresponding integrable hierarchy. In what follows, we call it the associated two-component chromosome hierarchy. So in the following, we will investigate how the Liouville transformations 7 affect the underlying correspondence between the flows of the two-component chromosome hierarchy and the associated hierarchies. Let's now consider the two-component hierarchy, chromosome hierarchy. First, the two-component chromosome system can be expressed in the bi-Hamiltonian flow with compatible Hamiltonian operators K and G in NAN, and the associated Hamiltonian functionals are H1 and H2. According to the classical Magritte theory, the Hamiltonian pair induce the hierarchy of bi-Hamiltonian system. The positive flows begins with the seed equation, and the two-component chromosome system is the second member. In the negative direction, observe that the Hamiltonian operator K emits a Casimir Hamiltonian HC, which leads to the Casimir system. Yes, the Casimir system. So, okay. Okay, so applying the inverse recursion operator to this first negative flow successively produce all members in the negative hierarchies. This is the two-component chromosome hierarchy. So what about the associated hierarchy? We will demonstrate it in the next lemma that the associated hierarchy is actually generated by this recursion operator R bar. Yeah. So successively applying R bar to the Euler seed symmetry, K1 bar produces the positive and negative flows of the two of the associated hierarchy. In particular, the first negative flow, the n is equal to 1 in the equation. Yes, in the equation 15, can be written in this explicit form, 16. Recall that the Lax pair formulation is transformed from the two-component chromosome by the Liouville transformations will give rise to this form. Yes, will give rise to this system. Obviously, it is not nothing but the first negative flow, 16. Furthermore, the second positive flow of the associated hierarchy is this system. Yes, is this system. So firstly, it can be obtained by the Y component of the former Lax pair together with this time part. Secondly, in this paper, in this paper of Ivanov and Lams, they introduce the following Lax pair, leading to this integrable system. Comparing these two, we found if kappa is equals 0, then the resulting system is exactly the second positive flow up to a change of variables. Yeah, up to a change of variables. Furthermore, final. Okay. So, okay, I'm sorry. Okay. Finally, a change of further dependent variables will convert the second the second positive flow into this system. Yes, into this system, which is exactly the so-called Bosniak system given in 1975. Okay, so far we can answer the first question. The associated hierarchy, which has the Liouville correspondences with the two component, with the two component chromosome hierarchy is initiated with the system 18, which is related to the Bosnian system up to such a change of variables. Yeah. The main result. The main result of the Liouville correspondences is given in this theorem. More precisely, under this Liouville transformations, for each positive integer n, the n+1 positive flow in the two component chromosome hierarchy is mapped into the nth negative flow of the associated hierarchy. In the positive direction, the nth members of the negative flow in two chromosome hierarchy is mapped into the n+1 positive members in the associated hierarchies. The proof of this theorem relies on two preliminary lemmas. The first one provides three operator identities. Based on this, we can arrive at this identity for the recursion operator of the two hierarchies. In the left-hand side, of this identity, K and G are the two compatible Hamiltonian operators for the two chromosome hierarchies. So G times K inverse is the inverse of the recursion operators for the two component chromosome system. While in the right-hand side, the R bar is the operator mentioned just now. We can prove that, prove that the R bar is not only the hereditary operator itself, but also the recursion operator for the associated hierarchy. Finally, based on this operator identity for recursion operators, we prove the final result on the Liouville correspondences by combining it with the recursion with the reciprocal structure in Liouville transformations, taking full advantage of the conservative structure of each flows in the two component chromosome hierarchy. For the time being, I won't go into more detail of the proof of the final theorem. Let us move on to the next topic. The next topic is the correspondences between the Hamiltonian functionals of the two component chromosome and the associated hierarchies. As is well known, and for an integrable system, the conservation laws plays a crucial role in the study of well-posedness, wave breaking, or stability of solid solutions. Hence, the induced relationship between the conservation laws for the integrable system with nonlinear dispersion and their corresponding solid counterpart turn out to be valuable for revealing the relevant structure of the former conservation laws. For the Hamiltonian system, one can construct an infinite hierarchy of Hamiltonian conservation laws. In particular, in the two-component Thomas-Holm setting, the Hamiltonian functionals Hn are determined by the recursion formula, the 21. Yeah, the Hamiltonian functionals, whereas for the associated hierarchies, the corresponding Hamiltonian functionals Hn bar satisfies 22, where K bar and G bar are expected to be two Hamiltonian operators admitted by the associated hierarchy. However, they are unknown. Yeah, they are unknown. So to investigate the correspondence between the Hamiltonian functionals, we should first figure out the effect of the Liouville transformations on the Hamiltonian operators. Here we can use the result from over a general transformations for a general transformation formula for Hamiltonian operators under a change of variables, which can be directly generated to the multi-component case. Assume these two n-component system are related by this coordinate transformation. Their respective Hamiltonian operators. I think, okay. Please wait me a moment. Can be okay. Okay. Their respective Hamiltonian operators dm and dq bar satisfy this identity, where T is n times n matrix operators with entrance Tig in this form, and T star is its adjoint operator. So direct of this theorem is to derive the Hamiltonian pair for the associated hierarchies. Yeah, associated hierarchy case. We get the Hamiltonian operators K bar, G bar in this form. Indeed, due to the transformations in this present setting, the gamma is low. Yeah, and the metric operator T, yes, take this form. We conclude that the resulting Hamiltonian pair for the associated hierarchy are K bar and G bar in this form. Yes, in this form. And hence the associated hierarchy can be written in the bar Hamiltonian form as well. Yeah, bar Hamiltonian as well. Here I'd like to give a remark. On the one hand, it follows from K bar and G bar that the resulting K bar times G bar inverse is exactly the R bar given, is exactly the recursion operators R bar given in the former lemma. On the other hand, the relation. On the other hand, the relations between G and K bar, K and G bar provide an alternative decompositions of the recursion operator R bar. Yes, the R bar. So, it's different. It is not the decomposition of the recursion operator R bar given in the formal lemma, which is necessary in establishing the Liouville correspondence for the two-component chromosome hierarchy. Now, with these two pairs of the with these two pairs of Hamiltonian operators in hand, we can we still need two lemmas. The first one clarifies the correspondence between the variational derivatives of Hn and Hn bar, and the second one provides a formula for the change of variational derivative under the transformation. Finally, combining these two lemmas produce the one-to-one correspondence between the sequence of the Hamiltonian functionals admitted by the two-component chromosome and the associated hierarchies. These are the Liouville correspondence for the two component chromosome hierarchies. Next, let's turn our attention to the Gengxue system. The Gengxue system admits three isospectral problem found by Professor Geng and Xue. It was shown by Li and Chai that these reciprocal transformations, together with the two dependent variable transformation, convert the isospectral problem of the Gengxue system into isospectral problem of this form. Yes, of this form. And the compatibility condition gives rise to this integrable system, which can be viewed as the first negative flow of the associated Gengxue hierarchy. It turned out that the Gengxue system is related to this first negative in the sense that their respective isospectral problems are related by these Liouville transformations. Similar as before, we generalize this result to their integral hierarchies and investigate the Liouville correspondences between the Gengxue hierarchies and the associated hierarchies. The Gengxue hierarchies can be written in this bi-Hamiltonian form with a pair of compatible Hamiltonian operators K and G. Based on the bi-Hamiltonian structure, one may construct the four Gengxue hierarchy, while the Gengxue system is exactly the second positive flow, while the negative flow is generated by the Casimir flow, by the Casimir system. When it comes to the associated hierarchies, one can construct its Hamiltonian pairs by applying the Liouville transformation from the given Hamiltonian pair for Gengxue system. Indeed, the resulting Hamiltonian operators are K bar and G bar in this form. Consequently, the associated Gengxue hierarchy can be obtained by applying the resulting recursion operators R bar to the seed symmetry G1 bar. The scheme then the scheme of Liouville correspondences between Gengxue hierarchy and associated hierarchy is described in this theorem, which show that there also exists an one-to-one correspondence between each flow in these two hierarchies. Okay, to prove this result, two preliminary lemmas are required. Okay, the first one provides three operator identities. Okay, and the second one clarifies these relations between the operators, between the recursion operators admitted by the two hierarchies. In this identity, the G times K K inverse in the left-hand side is the inverse recursion operators for Gengxue system. Then, okay, what are capital V and capital V and capital U in the right-hand side? The metric, okay, the matrix operators capital U and V, U and V takes this form. The one key issue is that we found that the recursion operator R bar is actually equal to the U capital U times capital V. But capital U is not K bar, and capital V is not G bar inverse. So this formula in red color can be viewed as a new operator factorization for the recursion operator R bar, which is not the same as the direct decompositions that R bar is equal to K bar times G bar inverse. If you check the proof of the Liouville correspondences, you will find that such a novel factorization plays a key role to identify the systems transformed from the negative or positive flows of the Gengxue hierarchies to be the corresponding positive or negative flows of the associated hierarchies. Similarly, as the two-component chromosome hierarchies and its associated hierarchies, we can also establish an one-to-one correspondences between the sequence of the Hamiltonian functionals admitted by the Gengxue hierarchies and associated hierarchies. Okay, I think I can stop here. Thank you for listening. Thank you, Nalini. Okay.
Thank you very much, Professor Liu. I believe there were some questions in the chat from George Chow. He had to leave early, so he wrote down the questions in a chat to me. He said, one is, what is the exact meaning of the Liouville correspondence? If it is a kind of transformation, is it invertible?
If it's invertible, what is the definition of the Liouville correspondence? This is the first question. Yeah. The transformation between the two isospectral problems of the two integrable hierarchies can be viewed as the Liouville transformation. based on such Liouville transformations, we expect to derive kinds of relationship between the integrability structures of the corresponding two integrable hierarchies. We called this such a relationship between the two integrable hierarchies under based on the Liouville transformations between the corresponding isospectral problems. Such a relationship between, for example, between the flows, between the Hamiltonian functionals in the two hierarchies, such a relationship is called the Liouville correspondence. Okay, so for the map, the map is the map invertible. I think I don't know, but we just now we can only to map the for example to map the two component chromosome hierarchy into the associated hierarchy. Right. Yeah, but so, involve so I don't know. Yeah.
The second part of his question is there any geometric structure in that correspondence, in the Liouville correspondence?
Yeah. So we believe there is a geometric meaning or geometric the characteristics for the Liouville correspondences, and this is our next goal of this study. Yeah, thank you. It's a very good question. Yeah.
Does anybody else have any questions? While we are waiting, perhaps I can ask some questions. I think when you first wrote down the Liouville transformation in your slides, for example, I think it was equation 19. Perhaps 19, you can go back to your slide.
Okay. 19.
Just near here. Oh, no, keep going.
Okay.
There.
Yeah, yes.
So we have, I can see that there is a transformation from X and T to tau and Y.
Yeah.
But I didn't see the definition of what is Y.
Y is the new variables of the associated hierarchy.
Oh, I'm sorry, I missed something. I can see it now. Y is the integral of rho. Yes. I'm sorry, I missed that. Okay.
That's okay.
But that was just a small question. But I have a bigger question, which is because I'm interested in the Panleve equations, which are reductions.
Nalini, I think I missed something. Could you please repeat your question?
Sure.
I missed something, yeah.
I'm interested in Panleve equations.
Yeah, okay. Panleve equations.
And those arise as similarity reductions of the KdV, modified KdV, nonlinear Schrodinger, and so on. So what are, have people studied these similarity reductions or other reductions of Kamasa-Home and two-component Kamasa-Home or associated hierarchies? Are there corresponding ordinary differential equations?
Ordinary differential, okay, I don't know. I don't know about, I don't know. I'm so sorry. Yeah.
No, that's okay. It's an interesting.
I'm sorry. I'm very sorry.
No. Please don't worry. It's just I have studied hierarchies of Panleve equations, and they come from.
Oh, it's very interesting. Yeah.
They come from hierarchies, reductions of, for example, the Sawada-Kotera also, and modified KDV and so on. So it's interesting for me to understand whether there are also reductions of Kamasa home hierarchies.
Oh, okay. Yeah. Okay, thank you.
Any other questions or comments from the audience? Please speak up or put up your hand or put it in the chat box. Maybe people are very shy today. So if there is no further comments or questions, I think we should draw this session to a close.
Okay.
Thank you very much, Professor Liu, for your talk. It was a lovely, clear, very interesting talk.
Thank you. Thank you for all the listeners. Thank you. Thank you for your question. Yeah.
No, thank you for your talk. And thank you to the audience members too for being flexible. And thank you for your direct messages as well. Okay, so I will now close the recording and the session. Goodbye, everybody. I hope you stay safe and healthy.
Okay. Goodbye. Bye.
Bye-bye.
Bye.